Okay, let's jump right in. We've got some fascinating sources you shared with us. Today, we're tackling, well, a really mind-bending idea.
Uh-huh.
What if dark energy, the stuff we think makes up maybe 70% of the universe, driving its expansion faster and faster, what if it just, well, isn't real?
Right. That's the provocative heart of it, isn't it? It stems from this recent relook at Type Ia supernovae data.
Yeah, the very data that kind of pushed us towards dark energy in the first place, back in the late 90s.
Exactly. The standard view, lambda CDM,
Hmm.
it assumes things are pretty smooth out there on the biggest scales, and it needs that dark energy.
But this other idea, timescape cosmology, it looks at the universe's like clumpiness,
Yeah.
all the galaxies and
And
voids.
says maybe that's the key. Maybe that structure explains the observations without needing dark energy at all.
Okay. So, our mission for this deep dive, figure out why we thought we needed dark energy, what this timescape thing actually is, what this new study is claiming, and crucially, what are the big counterarguments?
Sounds like a plan.
So, let's rewind. Why dark energy? Why did we invent it?
Well, it all boils down to measuring cosmic distances and how fast things are moving apart. We use these type E as supernovae, these specific stellar explosions.
Right, the standard candle.
Exactly. The idea is they always explode with roughly the same intrinsic brightness. So if you know how bright it really is and you measure how bright it looks to us,
You can tell how far away it is, simple enough.
theoretically, yes. But when astronomers did this for very distant supernovae, they found something unexpected. They were fainter than they should have been if the universe's expansion was, say, slowing down due to gravity.
Fainter means farther away.
Fainter means farther away than expected. It suggested the expansion wasn't slowing, it was actually speeding up, accelerating.
And gravity pulls things together, so you needed something pushing things apart.
Precisely, a repulsive force. And we gave it a name, dark energy.
Which leads us right to ACDM, lambda CDM, the standard model. Big scale smoothness plus this dark energy, often just a simple cosmological constant, lambda, making up most of everything.
Right.
Right.
And it's been incredibly successful because it's not just the supernovae. TDM also lines up beautifully with other huge pieces of evidence.
It's like the cosmic microwave background, the CMB.
Exactly. The heat left over from the Big Bang. It tells us so much about the early universe.
Yeah,
And also baryon acoustic oscillations, or BAO.
those are like cosmic ruler marks, patterns in how galaxies are spread out.
That's a good way to put it, standard rulers. And CDM fits the CMB data, the BAO data, and the supernovae data remarkably well altogether.
Okay, so that's the champion model. Very strong case. But now, enter timescape. It challenges that fundamental assumption, right? The smoothness.
It really does. It says, look, the universe isn't smooth. It's lumpy. You've got dense regions packed with galaxies, and then these enormous, almost empty voids in between. That difference matters.
And somehow that lumpiness makes it look like things are accelerating. How?
It's based on an effect from Einstein's relativity, gravitational time dilation. Clocks tick at different rates depending on the gravity around them. So imagine you're an observer inside a dense galaxy cluster, like we are. Our clock ticks at a certain rate. Now think about the vast expanding voids. They're much less dense, lower gravity. Time effectively runs faster there.
Faster in the voids, slower here.
Right. So light from a distant supernova travels through these voids for billions of years. It experiences that faster void time. When that light finally reaches us in our slower time region,
Uh-huh.
the cumulative effect, according to Timescape, is that the light looks dimmer, appears further away than you'd expect in a perfectly smooth universe. It mimics the effect we currently call acceleration due to dark energy.
So it's an illusion caused by comparing clocks in different parts of this lumpy universe.
That's the core idea.
And this recent study, the one reanalyzing the Pantheon plus supernova dataset, it found what?
It reported, and these are their words, very strong evidence favoring Timescape over KCDM, based purely on fitting that supernova data. They used a statistical method called Bayesian evidence and found a value suggesting Timescape was a much better fit for the SNA Ia.
Wow. Very strong evidence, just from the supernovae. That sounds like a big deal. But, I mean, the scientific community isn't just dropping dark energy yet, right? What's the catch?
Well, yeah, there's significant pushback.
Yeah.
The absolute main criticism, and it's a big one, is that this timescape analysis focuses only on the supernovae.
Ah, okay. Whereas CDM,
CDM's strength is its consistency across all the major datasets. Supernovae, yes, but critically, also the incredibly detailed measurements of the CMB and those BAO standard rulers.
and Timescape hasn't managed that yet.
Not even close, really. As far as the sources indicate, Timescape hasn't yet shown it could reproduce the specific patterns we see in the CMB temperature fluctuations or the precise scale of the BAO wiggles with anywhere near the accuracy of ACDM. That's the major stumbling block.
And I guess modeling a universe that's fundamentally clumpy is just hard mathematics.
Extremely difficult, yes. Making detailed testable predictions across all those different types of observation is a massive theoretical challenge for Timescape.
Plus, aren't some new results, like from DSI, hinting dark energy might be changing over time, which is different from it not existing at all?
Exactly. That's another active area. Maybe dark energy is real, but more complex than just a constant.
Okay, so let's try to sum this up. We have this provocative study, reanalyzing supernova data, finding statistical favor for Timescape, this idea that apparent acceleration is an illusion from cosmic structure and time differences.
But, and it's a big but, the broader scientific view holds firm for now. Dark energy, or something very much like it, remains the leading explanation, because ETCDM fits the whole sweep of cosmological evidence: CMB, BAO, supernovae, large-scale structure.
Timescape has some serious explaining to do on those other fronts.
Definitely. Huge hurdles remain, especially the CMB and BAO fit.
Still, it's pushing the boundaries, making everyone re-examine the assumptions.
Absolutely, and that's healthy for science. It forces us to ask, is ECDM maybe just a really good approximation? Are we maybe missing something fundamental by smoothing over the universe's true, complex, lumpy nature?
Yeah. What will new telescopes, like Euclid or the Roman Space Telescope, tell us? Will they finally pin down dark energy, or maybe reveal the illusion?
That's the exciting part, isn't it? Something
Yeah.
for you to ponder. Are we seeing the whole picture or just the simplified version?